Okay, very good. Yeah, thank you so much for the kind introduction. Thank you so much for having me on this webinar. Looks like it's the first one this year, so I'm happy to start this off, and hopefully I'm not disappointing anybody. So what I'm going to talk about today, and Joe already mentioned it, is the oxygen evolution reaction. And for those of you who don't know, it's a very critical and important part of water splitting or just using fuel cells that run on hydrogen. So um, no, my slides don't advance. What's going on here? Here we go. So before we dive into it, I just want to give you a brief overview of what my research group does in general here at the University of Houston. So we specialize on doing high performance computing for materials and materials properties that we can predict from first principles. And we use tools that allow us to give us statistically significant predictions. So we get error bars and ranges of values that one would expect. We use that to rapidly explore material space and look for materials with the right properties. And in this context, it's going to be catalyst for oxygen evolution reaction. We either work closely together with experimentalists to validate the performance of the materials that we're predicting, or some of the experiments we're doing in-house, for which we're using a temporal analysis of products reactor, which is a transient kinetic characterization technique, which is very nice and very complementary to using density functional theory and microkinetic modeling. So altogether, we focus on the computational aspects, but we always try to find close collaborations with experimentalists. Now, today, how is the presentation going to fit and align with the Energy Transition Institute? So I'll be talking about hydrogen generation and use of hydrogen. And of course, I'll be focusing on science, engineering, and technology aspects of this technology. Now, why are we interested in hydrogen? And there's many reasons. I'll just say a few that align with what I want to talk about today. So hydrogen is very interesting as a clean energy carrier. One of its big advantages is its very high gravimetric energy density. So in whatever form, liquid or compressed hydrogen, we get a very high gravimetric energy density. Unfortunately, the volumetric density is not so great. So you still need large volumes of hydrogen storage if you're storing it in liquid or compressed gas form. But on a weight basis, you can store a lot of energy. When we use hydrogen, we have very clean combustion. The only combustion product is water. Hydrogen is very versatile, so it can be used for power generation, but also in transportation, and it's used and required in many industrial processes. Storage and transport, well, that can both be seen as an advantage and maybe even a disadvantage. So transporting compressed gas hydrogen or liquid hydrogen is maybe not so simple. But the nice thing about hydrogen is that it really can be transported in both gas form or compressed gas, liquid, or it can be stored in chemical compounds. So one example might be ammonia. So ammonia is thought of being a good hydrogen storage or carrier. So there's many opportunities to come up with a good storage and transport scheme for hydrogen. And of course, hydrogen can be produced renewably, which is another great reason to look at it. Now, when hydrogen is produced or consumed, we typically, or we are looking at electrochemistry here. So the most common example that I'm showing you on the left is just a fuel cell. And so we have fuel that would be hydrogen going in. Molecular hydrogen is then dissociated into two protons, which dissociate or migrate through a proton exchange membrane. The electrons go through an external circuit and produce work. And on the anode side, on the cathode side here, then hydrogen then recombines with oxygen, forms water, and along with these electrons. So that drives the electrical current. Now, unfortunately, these fuel cells, and if you operate them in reverse, you have an electrolyzer, are not perfectly efficient. And the problem with those, the main problem is the overpotential. So when we split water, or we use hydrogen for the generation of electricity, we get a cell potential of 1.23 volts. That's the equilibrium redox potential between water and hydrogen. And so these 1.2 volts is the ideal value, ideal amount of ideal potential that we would like to achieve. Now, unfortunately, there are other processes that introduce losses. And so there's an activation potential, activation over potential that reduces the actual voltage that we can obtain. Then there are ohmic over potentials. And if you're running at very, very, very high current densities, then you can also have concentration over potentials or mass transport limitations. I have another graph here that shows the first two in a little more detail. So there's a thermodynamic over potential and then a charge transfer or sort of a kinetic over potential. So these two are potentials that we can look at very carefully and try to avoid them or minimize them through the design of very active anode or cathode materials. Now for water splitting, we need to be looking at the anode side then, and that is where the oxygen evolution reaction occurs. So this is now the picture of running it in reverse. We're feeding water in. Now at the anode, the water dissociates. We get protons that move over to the cathode where hydrogen is produced. So that's our desired product. And on the anode side, we then have oxygen left over. Now, it turns out that the oxygen recombination or the evolution of molecular oxygen is the part of this process that requires the most overpotential. So it has a lot of limitations. And so a lot of the research efforts need to be focused on finding these anode materials that are beneficial and lower the overpotential. Now, why is there a overpotential on the anode side? And so I apologize. This is going to become a very busy slide, but I'll do my best to explain it as good as I can. Now, what I'm showing at the bottom here is a stepwise sequential mechanism for the activation of two water molecules. So the first water molecule adsorbs, and on the anode surface, it forms an OH and it loses a proton. And that proton goes into the electrolyte, so into solution, and one electron moves or is pushed through the exterior electrical circuit. Now, in the next step, the second proton is missing, or the second proton is dissociated and goes into the electrolyte. And then in a third step, we have another water molecule that adsorbs now, forms an OOH intermediate, and the third proton and the third electron is released. And then in the final step, we have the O2 molecule and 4 protons. And then if these protons recombine on the cathode, we have the H2 formed. So it's a 4-step process. 4 electrons are exchanged. And each one of these proton-electron transfer steps ideally should have an energy change of 1.23 volts. That should be the potential. And so if we are talking about energy, if one electron is exchanged at the potential of 1.23 volts, we talk about 1.23 electron volts, and that's a unit of energy now. So each one of these step heights should be exactly that 1.23 eV. Now, unfortunately, there isn't a known catalyst that has the exact same energy levels at all of these intermediate states. If there were, then what happens if you are applying the potential of 1.23 volts, the ideal one, we get a completely flat potential energy diagram. So there would be no changes in energy as we are going from left to right and go through that reaction. Now, realistic materials, now shown here with the solid line, they have stabilities that greatly differ from the ideal ones that I've shown here in the dashed lines. So if these energy states deviate, then also the energy differences between two states deviate. So here, for example, between step 2 and 3, there is a energy change indicated, delta G RDS, for the rate determining step. And that is now much larger than the 1.23 volts. If we apply the potential and all of these energy states move along with that potential, and we're trying to approximate this perfectly flat line, well, what you see is that you need to apply an additional driving force for the reaction to proceed from state 2 to state 3. And so this is the origin of the overpotential for the oxygen evolution reaction. Now, I don't want to go into all of these different equations, but the bottom line here is that we can estimate the energy levels, the Gibbs free energies on all of these states, so state 1, 2, 3, 4, based on the energies of the intermediates that are absorbed on the surface. So that would be the OH intermediate here, the oxygen atom here, the OOH intermediate. And we need to know the chemical potential of hydrogen and the chemical potential of water. The other terms here are corrections for temperature, entropy, and things of that sort. Now, the chemical potential of hydrogen can be easily estimated with a theory that introduces the computational hydrogen electrode. So here we can assume an equilibrium with H2, which then forms a proton and an electron. For the proton, we can then add corrections that involve the pH of the electrolyte. The electron chemical potential is modified with the applied potential. So that is the EU term that changes the energy levels here. And then we can look at the energy differences and define an overpotential. So if we can estimate the stability of all of these intermediate states, we can very quickly estimate what the overpotential of the reaction would be. Now, next, there is a linear scaling relation between some of these intermediate states. And the most prominent one is the scaling relationship between the state that has the OH on the surface and the OOH on the surface. So these two intermediates look relatively similar to each other when they're adsorbed. And if one looks at the Gibbs free energy of the OOH intermediate and plots it versus the Gibbs free energy of the OH intermediate, and you look at a number of different materials, you find that they, by and large, follow some sort of straight linear relationship. And here, the straight line was fitted to have the exact same slope for both of these two species and an offset of 3.26 EV. Now that 3.2 EV is the difference between these two states. And now it doesn't really matter which material you're going to take. Any material along this line will have an energy difference of 3.2 volts between two steps. Now, if you paid attention, each step should have an energy difference of 1.2 volts. So for two steps, it should be 2.4. That leaves now a difference of 0.8 volts that is always required, or that separates these two states. And that difference of 0.8 electron volts divided by 2 ends up as being 0.4. And that is a overpotential wall. And I'll show that again in other slides coming up. Now, it is not just the OOH and the OH intermediate that scale linearly. In current work, we are looking at other intermediates as well, also for the chlorine evolution reaction. And so we find linear scaling relationships also with chlorine, for example, or the ClO. Oxygen looks a little bit more random. So oxygen does not follow a perfectly nice and straight linear relationship. But we are in the process of being able to explain why these deviations are occurring, and are in the process of developing a model that can also fully predict the oxygen binding energy as a function of the OH Gibbs free energy. So now coming back to this overpotential. So these linear scaling relationships between OOH and OH, they have been widely reported for over 20 years. What that now enables us to do is to look at or estimate the potential, the overpotential, by simply knowing the binding energy of oxygen and the binding energy of OH of any material. And if one plots that, one sees that a volcano-shaped activity plot is obtained. So on the y-axis, it's the overpotential, but you could also have the current density as a function of this descriptor. And the descriptor is the difference between the oxygen and the OH Gibbs free energy. Now, what you also see here now is that there are some materials that are near the top of the volcano, but there is nothing that is exactly at zero. So there is no material that even approaches an overpotential of 0. And the overpotential wall, I previously cited a number of 0.4, right? So that would be right here. But there are some materials that deviate from this relatively general scaling relationship. And so now there have been reports with overpotentials close to 0.2 EV, but it's getting harder and harder to find better and better materials. So the linear scaling between the surface species really imposes a limit on the maximum oxygen evolution activity, but it can also be used for rapid material screening, and that's what I would like to talk about mostly in this presentation. So computational catalyst screening, there is, the second edition of the book Computational Catalysis, for which I wrote the opening book chapter, was just released earlier, I think in December 2024, so 2 months ago. And so it describes the process, but I just want to highlight a few things or the ideas. So a lot of it is simply, it's based on the Sabatier principle. So the Sabatier principle invokes this idea of these volcano plots again, or these simple activity plots that show a maximum at an optimal descriptor value. And the descriptor value can be a bond strength of an intermediate on the surface, or as we have just already seen, the difference between an oxygen and OH binding energy on for the oxygen evolution reaction. So the descriptor varies from reaction to reaction, and then we have the catalytic activity. Now, why do we get these two areas where we get less activity? Well, if we have, let's say, a catalyst or an electrode that binds all of the intermediates very strongly, well, then nothing comes off the surface. We just get surface poisoning and we get an inactive surface. If our surface interacts very, very weakly, then we don't have any adsorption. Then we have essentially an inert material in solution or in the electrolyte, and there's no reason for any of the reactants to adsorb. So there's a happy optimal value somewhere in between. But for each different reaction, it's always the question, well, what is the descriptor, right? And what is the right value for that descriptor? What does it mean to bind these intermediates just right? So when we started this, I was very lucky that Richard Tran joined my group here at the University of Houston. So he's depicted here in the bottom left. He's been a postdoc for, I think, just over a couple of years now. And in his previous assignment, he worked with Zach Ulissi at Carnegie Mellon University, and they collaborated with Facebook or Meta AI to develop the Open Catalyst project. So in the Open Catalyst project, there is a database for metals, but then the one that Richard developed is for metal oxides. And it was developed with the intention to look at water splitting and fuel cells, batteries, hydrogen production, equilibrium, shapes of nanoparticles, and so on. Now, we try to use this database to accelerate screening for new oxide materials that can catalyze the oxygen evolution reaction. And what we need for that is we need to be able to, we need to predict the surface energy of a material, the surface free energy. We want to predict the overpotential or the activity of a material. And to do these things, we need to be able to estimate the energy of the surface. We need to estimate the Gibbs free energies of oxygen, OH, and OOH on the surface of these different oxides. So that's what we need to do. And we used the OCP database and one of its machine learning models that is available that comes with it. And the one that we picked is the GemNet OC. There is a slightly better model available now. It's the Equiformer V2 model, performs slightly better. But when we started this project, the GemNet OC was the best machine learned model based on the data set. It is essentially, or it is derived from the data set, from the OC20 data set that includes all metals. And it is fit to predict structure, energies, and forces. Now, the model is relatively good when it comes to materials that it's been trained on. So the mean absolute error for materials within the training domain is less than 0.25 electron volts. And that is not too bad. Typical error estimates for a DFT calculation are also at between 0.1, 0.15, sometimes 0.2 eV. So it's reasonably good. But unfortunately, the out-of-domain error is rather large. So the 0.92 is a little bit larger than one would desire. The big advantage of this machine learned model is, of course, its runtime. And so we can make a prediction every 5 seconds. Whereas if we did this prediction with density functional theory at a much higher level of theory, of course, we get more reliable numbers. However, it would take maybe a minimum of 5 hours, maybe even up to 5 days to get these results and make a single prediction. Now, we always get asked, like, well, if you already have the OC22 dataset, why can't you just screen that and work with that? Well, the OC22 dataset was created with the intent to train a ML model. So there were random combinations of surfaces, so slabs, adsorbates, and coverages chosen. And that was done to have a relatively large training domain for the machine learning model. If we now go into this database and look at the materials where we have the binding energy of OOH, the binding energy of oxygen, and the binding energy of OH, and we look at the overlap, then there's only 86 materials for which all of these binding energies are available. And so that's obviously not the amount of data that we wanted to investigate. So we went ahead and we increased the database, and we looked at all of the materials that are in there. We cut a bunch of surfaces and looked at their stabilities and different terminations. So we ended up with almost 50 different surfaces for each one of these materials. We needed to then calculate the adsorptions of OH, oxygen, and OOH. And we did limit ourselves to surfaces that have a maximum Miller index of 1 somewhere. So with all of that, we still ended up with now almost 6 million calculations that we needed to, or over 6 million calculations that we needed to perform. And we could rely on linear scaling. So we could say, well, instead of calculating the OOH binding energy, we could skip that for now and just use that linear scaling relationship that I've already introduced. But if we do that, we would be unable to find and identify candidates that might actually break this hard limit of the 0.4 volt over potential. So if we want to look for outliers that do not follow that linear scaling relationship, well, then we have to actually find those, and we can't do that if we're not calculating them. So we did that. So we have these over 6 million calculations. If that takes 5 seconds per calculation, you still need approximately 1 year of supercomputing time to get it all done. Now, we didn't wait for 1 year to start looking at everything. So many of these calculations were submitted in parallel and were running side by side. And so we can get a lot of these things done faster and don't have to wait 1 year to see all of the results. But I just wanted to give you an idea of how computationally expensive this is, despite using machine learning and high performance computing. Now, with this machine learning model available, we went ahead and we collaborated very closely with Shell here and defined a screening defined several screening criteria that allow us to find new or interesting materials. So we begin with that OC22 dataset. We look at materials that are stable under the reaction conditions. We introduce a new criterion. I'll get to that. That's really a pretty cool idea that Richard had here, and that's nanoscale stability. I'll elaborate on what that means. Then, of course, we want to look at active materials. We can include some extra materials that are metastable, and obviously we do want to have cheaper materials in the end, so we can look at the cost of these materials as well. So to give you an idea, what is the OC22 dataset? What are we looking at? So we have pretty much all of the elements here that are shown in blue. We've got oxygen in here, of course, because we're looking at oxides. So we have a pretty good number of data or materials to begin with. So it's over 4,000 combinations of these materials. They can all be found in the materials project. And that's our starting search domain. Now, for each of these materials, we need to make sure that they actually survive in the conditions that are encountered in this electrochemical environment. Now, after a few refinements and going back and forth, we agreed with Shell that we want to look at acid medium. So we have pH 1. We are looking at an applied potential of 1.8. So why not 1.2? Because, well, we know there's going to be an overpotential. And if you want to get to higher current densities, you need to apply a little bit of extra voltage as well. So we looked at stability for an applied potential of 1.8 volts. And we looked at temperatures at 80 degrees C. This paper is already published. We have varied some of these stability criteria, and so it affects some of the materials, but by and large, it has a relatively small effect on the number of materials that we identify. Now, we assumed that we can look at materials that are unstable with respect to the decomposition in acid media up to 0.5 EV. And we decided to allow that. So we are not looking only for perfectly stable materials. We're looking at materials that are unstable or metastable, because surfaces can passivate and there's a barrier for decomposition. And so some of the materials that are not absolutely thermodynamically stable can still remain metastable. My favorite example to mention here is that I do enjoy going into the woods and go for hikes in forests. And if we're considering this only as a thermodynamic state, then forests are very unstable. And we've seen this in LA, the thermodynamically more stable state of a forest if it burns down to CO2 and water, essentially. So that happens, but it's somewhat rare, fortunately. And so in the context of these materials, we can look at some materials that can be preserved in their actual phase, and they would be protected with surface passivation. The next thing we want to look at now, if we have the bulk stable per base stable materials, how many materials or which surface facets will be stable and which surface facets can we look at? And so this slide is very dense and very complicated, but I'll try to walk you through it. So the wolf construction, and we're showing a few examples here on the left, bottom left side, is a technique. It's a geometric technique that allows us to estimate the shape of a nanoparticle if we know the surface free energies of the different facets. So what varies here between these three different scenarios is that the surface free energies of the different colored facets has been changed. And depending on what these surface free energies are, we get different shapes. Have you ever seen a nice basalt rock formation with this very beautiful hexagonal shape? That's essentially what we're talking about here. So the HCP crystal structure of a basalt has planes of very low surface free energy. And those are the ones that end up forming these nice hexagonal shapes. But for many other crystal structures, geometries, you'll find different shapes, obviously. Now, we can estimate the surface free energy, that's gamma, as a function of the oxygen chemical potential and the chemical potential of the metals. And so we can vary those, and we have an equation here that we can use to estimate the surface free energy. And then we can go into this graph. This is a Pourbaix diagram where we look at a pH, and we said we wanted to look at pH 1, and we want to look at a certain potential, and that's 1.8 volts. And wherever we land in this graph, we come into a color code, and the color code then corresponds to a surface termination. So the surface termination here in cyan would be pretty good here on this side. Now, if we are looking at the material over here, we have the red termination, and that's the one that we're showing right down here. The difference between these two is the metal chemical potential in both cases. So we can estimate that also based on our machine learning model. The next thing we want to look at is obviously the activity, which then translates into the overpotential. So the activity or the overpotential is determined by looking at the delta G, or the differences of the Gibbs free energy between the different states along the mechanism of the hydrogen evolution reaction. And maybe you recall the potential energy diagram that I showed in the beginning. So we calculate or we use machine learning to estimate the energies delta G1, delta G2, delta G3, and delta G4. And then we are looking at the differences between these states. And we look at which one of these steps has the highest energy difference. And from that step, we can then extract the overpotential or the difference between the Gibbs free energy of each state versus the ideal value of 1.23. And that tells us how active a material would be. So at this point, I want to maybe highlight, we started with just over 4,000 bulk materials. We narrowed it down to 1,800 that were stable in the, or metastable in the conditions we are considering. Then stable surfaces, well, there were only 1,500 materials with stable surfaces, but those materials then had multiple different terminations or facets that can be exposed. So now we're now we're up to 12,000 surfaces that we need to look at and estimate the activity. And now we're filtering it out down to just the materials that are somewhat active. And for activity, we use the cutoff of 0.75 volts as the overpotential. So that leaves just about 100 materials again and 512 surfaces. The next criterion is to just look at metastability. So this would be solid state stability, comparing the stability of these materials versus their decomposition products. That was done very quickly using the data in the materials project. If you open that, you can actually find these values almost in a tabulated form. And we looked at materials that have a stability above Hull within 0.1 EV. And then we eliminated some of the materials that are extremely expensive. And for that, they are mostly the iridium-based materials. So ruthenium dioxide, which is a known good catalyst for the oxygen evolution reaction. Not quite as good as iridium oxide, but the prices are pretty shocking. You can buy a nice car for the price of just 1 kilogram of iridium dioxide. We looked at the prices. They evolve over time, obviously. There was a low point for ruthenium dioxide of just $8,000 per kilogram, and so we used that as a cutoff value. And we came up with a final list of candidates now, and there is 81 that passed our screening results. And the formulas of these materials are just shown here. We report the number of facets. So sometimes a material exposes just one facet that's active, but we would like the material to be active on multiple facets. So 2, 3, 4, the more facets are active, the more of the surface area of the particles will actually contribute to the chemistry. And we have some materials that are really promising with an overpotential of just 0.18 or 0.21 that are also not extremely costly. And so some of these materials are being tested and verified, but I expect that that probably most of these materials are not going to perform just as well as we think they do. Now, we ended up with 81 materials, but what we noticed when we looked at the screening process is that one of the biggest filters is really just the stability. And so the first step that we looked at for base stable materials, that eliminated more than half of the candidate pool. I think it's like 65% of the candidates just are not, can no longer be considered because they're just completely unstable under these conditions. And we're not alone. There's 2 other papers, both in ACS Energy Letters, that looked at stability for acid stable oxygen evolution, and also looked at the poor base stability as well as the energy above Hull. So that's the energy versus decomposition to the elements or the binary oxides. And so looking at that, in these papers, they also screened the database with slightly different criteria, and they found only 68 stable materials, but began with 47,000. So it's a huge down selection criteria just looking at the activity. And then if you're looking at somewhat active materials, there's only 17 left. So the problem is that the stability eliminates a lot of the oxides. And so we wanted to see if we can find materials that are really active and then see if we can make them stable. So this is the idea now. What I'm showing here now is just the overpotential assessment of the eliminated oxides. So the oxides we're not considering anymore. And the ones that have a blue color code here in this graph are those with a very low overpotential in the bottom right part. In the top left triangle, the red numbers or the red ones are those that have many facets that are active. And what we're looking at are oxides that contain these elements that are shown on the X and the Y axis. So the idea was now, are there very active oxides that we have eliminated because we thought they're unstable? And if they exist, can we think of ways to stabilize them? And so here's where Richard Tran became very creative, and he looked at nanoscale stability. So what we looked at was just the bulk stability of a material. And the bulk really has a lot of volume, but not much surface area. Now, if you're going to smaller and smaller particles, well, the surface area or the ratio of surface to volume becomes much, much larger. And so if we're taking this cube here, the surface to volume ratio is 2, whereas in the smallest cube here, the surface to volume ratio is 6. And if the surface free energy is very different from the bulk volumetric energy, you get these two different lines where at, let's say here, at very large diameters, a material is stable. But when you're getting smaller and smaller and smaller, the bulk becomes not so stable, but the blue line takes over, and that would become a nanoparticle. So some materials do exist as a nanoparticle. Other particles cannot be stabilized as nanoparticles. The equation is shown here, and so what we have is the energy as the volume energies, the bulk energy that's multiplied with the volume, and here we're using the volume of a sphere, and then that's the surface free energy multiplied with the surface energy of the particle. And so now if we're changing the radius, this contribution scales with r squared, and this contribution scales with r cubed. And so we can look at the surfaces. We can build these wolf shapes again of these nanoparticles, look at their surface to bulk ratio, and on the surface we have also the different terminations. We get the fractional area of each of those planes. We know their surface stability, and we can estimate how stable a particle is if it's not in the bulk but exists in a smaller size. Now, there are certain materials now that we found where as long as the particle radius is relatively small, so 400 angstroms, that's 40 nanometers. So if we get something as small as 20 nanometers, there are some materials where different phases or different materials become stable, but only at the nanoscale. Now, if we consider that, we are now reanalyzing our workflow. And so if we now follow the materials on the left-hand side, instead of just having 1,800, we were able to find 2,700 materials that are pro-base stable. So that's almost 1,000 materials more. So 25% of the initial candidate pool has now been added as a nanoscale stable material. And then we go through the same process. And we end up with 120 materials versus 80. Still doesn't sound great, but overall it's a 50% increase in the number of materials that could be considered. So from 80 to 120. And here's a list of these materials. Again, some of them have a very low estimated overpotential. And all of these materials were previously eliminated because their poor base stability is 0.5 and higher, which was our cutoff criterion. But at the nanoscale, they would be stable. Now, we did do a DFT validation, and there is pretty good agreement. There are some outliers or some machine learning predictions that were just simply lucky, I have to admit. After closer inspection, the machine learning prediction should not have worked, but it did. But what's important is that if we're looking at the overpotential we estimated from machine learning versus the overpotential we estimated from DFT, we do find that most of the materials that were identified from machine learning still have an overpotential of less than our cutoff criteria of 0.75 when we're evaluating it with DFT. But there is some deviation here. So it's not a perfect model by no means, but it worked reasonably well. Okay, so the summary here is that we did create a database of machine learned total predictions for forces or energies of bare and adsorbed surfaces. We use that to predict overpotentials, wolf shapes, and from that also the nanoscale stability of materials. If we had used only DFT, that would be completely impossible to do. And so it was only because we had this ML network available. And without looking at linear scaling constraints, we were able to find 80 candidates or 81 that are pretty good for OER, and an additional 40 candidates when we're considering nanoscale stabilization.